For eons, humanity has gazed upon the night sky, wrestling with the most fundamental of all questions. Where did it truly begin? Our modern cosmology offers a spectacular answer: the Big Bang, a singular cataclysmic event that forged space-time, energy and matter from an unfathomable point. It is the Genesis story etched into the very fabric of our observable universe. But pause for a moment. If every effect we observe, from a falling apple to a collapsing star, has a preceding cause, then what sparked that initial cosmic firestorm? What orchestrated the Big Bang itself? Was it the absolute zero point of creation, or merely the grand overture to a symphony already playing in an older, vaster cosmic theatre? This is the first cause paradox, an intellectual crucible that melts away comfortable certainties. It forces us to confront a profound truth. Our most comprehensive scientific models, while elegantly describing what happened after the Big Bang, fall silent when asked about the before. Join us as Terran journeys into the ultimate cosmic mystery. If you're ready to question the very foundations of reality, subscribe now and become part of a community dedicated to understanding our place in the infinite cosmos. Let's begin. At the heart of modern cosmology lies the magnificent narrative of the Big Bang, a scientific epic that chronicles the universe's journey from an unimaginably dense, hot state to the vast, intricate cosmos we inhabit today. It is more than just a theory. It is the reigning paradigm meticulously constructed over decades of observational triumphs and theoretical breakthroughs, explaining an astonishing array of cosmic phenomena. This model, often called lambda CDM, after the cosmological constant lambda representing dark energy and cold dark matter, stands as humanity's most robust framework for understanding our cosmic genesis. Our journey begins not with an explosion in pre-existing space, but as an expansion of space itself. Imagine, if you can, a cosmos condensed into a point smaller than an atom, possessing infinite density and temperature. This is the fabled singularity, a mathematical construct where the known laws of physics cease to apply. Within this primordial crucible, all the energy, matter and space-time of our universe were compressed, a state so extreme it defies human intuition and conventional description. It's not merely a before, but the very origin point of causality as we understand it, where the countdown to cosmic history truly began. From this enigmatic beginning, the universe underwent an instantaneous and spectacular burst of expansion known as cosmic inflation. Occurring within the first tiny fraction of a second, perhaps 10:01:36 to 10:01:32 seconds after the Big Bang, this epoch saw space expand by an astonishing factor of at least 10^26. This isn't just fast, it's a scale shift beyond comprehension, stretching the nascent universe from a subatomic speck to macroscopic proportions in less time than it takes light to traverse a single proton. Inflation was a profound theoretical leap, resolving several critical issues within the earlier Big Bang models, such as the horizon problem, which explains the surprising uniformity of the cosmic microwave background across vast distances, and the flatness problem, detailing why the universe's geometry appears so perfectly balanced. Following this dizzying period of inflation, the universe continued its rapid, albeit more gentle, expansion, cooling as it did. For the next few microseconds, the cosmos was an incandescent, swirling maelstrom of fundamental particles, quarks, leptons and their antimatter counterparts, along with bosons mediating their interactions. This superheated, dense medium is known as the quark-gluon plasma, a primordial soup where matter could not yet coalesce into stable protons and neutrons. The sheer energy of this environment meant particles were constantly popping into and out of existence, a quantum dance of creation and annihilation governed by unimaginable temperatures and pressures. As the universe continued to cool over the next few minutes, the conditions became ripe for a pivotal event: Big Bang nucleosynthesis, or BBN. At temperatures hovering around 1 billion degrees Kelvin, protons and neutrons could finally fuse, forming the nuclei of the lightest elements. Within the first 20 minutes, almost all the universe's hydrogen, helium, and a trace amount of lithium were forged. This precise cosmic cooking process provides one of the strongest empirical pillars for the Big Bang, as the predicted ratios of these light elements precisely match what astronomers observe in the oldest, most pristine parts of the universe today, a testament to the model's predictive power. Yet, for hundreds of thousands of years, the universe remained an opaque, superheated fog of ionized plasma, impenetrable to light. Electrons, still too energetic to bind with atomic nuclei, constantly scattered photons, preventing any clear vision. Then, roughly 380,000 years after the Big Bang, the universe cooled to approximately 3,000 Kelvin. This critical temperature allowed electrons to finally combine with protons and helium nuclei, forming the first stable neutral atoms of hydrogen and helium. This event, known as recombination or decoupling, dramatically changed the universe's transparency, allowing photons to travel freely for the first time. These ancient photons, stretched and cooled by billions of years of cosmic expansion, reach us today as the cosmic microwave background, CMB, radiation. It is the universe's baby picture, a faint uniform glow detectable from every direction, providing an unparalleled glimpse into the conditions of the early cosmos. The tiny temperature fluctuations within the CMB, meticulously mapped by missions like COBE, WMAP, and Planck, are the seeds from which all future cosmic structure would grow. After the CMB, the universe entered a period aptly named the Cosmic Dark Ages. For hundreds of millions of years, there were no stars, no galaxies, only vast expanses of neutral hydrogen and helium gas, drifting silently through the expanding void. This era represents a significant informational gap, a time before light could effectively penetrate, challenging our observational capabilities even with the most advanced instruments. It was a quiescent, unlit epoch, yet beneath its serene surface, the slow, relentless pull of gravity was already at work, drawing together slight overdensities of matter, preparing the stage for the next grand act of cosmic evolution. This gravitational assembly eventually ended the Dark Ages, igniting the first stars, the population 3 stars, perhaps 200 to 400 million years after the Big Bang. These colossal, short-lived behemoths were formed purely from hydrogen and helium. Their fierce nuclear furnaces and subsequent violent supernova deaths enriched the surrounding gas with heavier elements, seeding the cosmos for the next generations of stars and, crucially, for the formation of the first galaxies. These early galactic nurseries then merged and grew, forming the intricate cosmic web of clusters and superclusters that define the large-scale structure of the universe we observe today, a structure whose formation is remarkably consistent with simulations based on the Big Bang model and the influence of unseen dark matter. The observational evidence for the Big Bang is overwhelming and multifaceted, extending beyond the CMB and light element abundance. Perhaps the most foundational piece of evidence is the expanding universe itself, a discovery attributed to Edwin Hubble in the late 1920s. He observed that distant galaxies are receding from us, and the farther away they are, the faster they appear to be moving, a phenomenon known as Hubble's law. This isn't galaxies flying through static space, but space itself stretching, carrying galaxies along with it, much like dots on an inflating balloon. This redshift of galactic light, an undeniable signature of expansion, provides the dynamic backdrop for our entire cosmic story. Furthermore, the Big Bang model, when coupled with the existence of dark matter and dark energy, successfully predicts the distribution of galaxies and galaxy clusters on the grandest scales. Simulations show that the gravitational scaffolding provided by dark matter naturally leads to the formation of the cosmic web, a vast network of filaments, walls, and voids that mirrors the observed large-scale structure of the universe with remarkable accuracy. The influence of dark energy, a mysterious force accelerating the universe's expansion in more recent epochs, further refines this picture, explaining why the cosmic ballet continues to pick up pace. So, the Big Bang stands as our cosmic narrative, a powerful and predictive account of how the universe evolved from an infinitesimal point to its current majestic form. Yet, for all its explanatory power, the Big Bang model, in its current form, does not explain itself. It describes the universe's evolution from an initial state, but not the origin of that state. It offers no insight into the nature of the singularity, nor what forces or conditions might have existed before it, if before even holds meaning in that context. This is where the scientific narrative reaches its profound limit, where the first cause paradox truly begins to loom, beckoning us to venture beyond the established framework into realms of deeper, more speculative, and ultimately, more awe-inspiring inquiry. The Big Bang, for all its explanatory power in describing the evolution of our universe, presents a profound, almost uncomfortable silence when pressed on its ultimate origin. It provides a detailed account of what happened from an initial moment, but it offers no definitive answer to the quintessential question: why did it happen? Or what precipitated that initial singular event? This is where the universe's grand narrative collides with humanity's most ancient and persistent intellectual challenge, the first cause paradox. Our minds are instinctively wired to seek causality. From the simplest falling leaf to the intricate dance of planetary orbits, every phenomenon we observe in the cosmos appears to be an effect of some preceding cause. This fundamental principle of causality underpins not only our everyday understanding of the world, but also the entirety of scientific inquiry. Science operates on the premise that natural phenomena have natural explanations, that given enough data, we can trace a chain of cause and effect back to an antecedent event or condition. It is this relentless pursuit of causes that has allowed us to unravel the deepest mysteries of the universe, from the structure of atoms to the dynamics of galaxies. Yet, the Big Bang, as the proposed origin point for space, time, and matter itself, defies this intuitive and scientifically robust framework. If the universe, in its entirety, began at a specific moment, the Planck epoch, a fleeting 10 to 43 seconds after the Big Bang, beyond which our current physics models collapse, then what existed before that moment? What force, mechanism, or entity could have initiated the very fabric of existence? This is not merely an event within the universe, but the event of the universe, an unprecedented genesis that seems to stand outside the very causal chains it subsequently unleashed. The paradox deepens when we consider the concept of nothing. In common parlance, nothing implies a complete absence of anything. But in the context of the Big Bang, nothing is far more elusive and fraught with conceptual difficulties. Does it mean an empty void, a vast expanse of darkness waiting to be filled, or does it refer to a state devoid of space-time itself, where even the concepts of before or empty lose their meaning? If there was truly nothing, no space, no time, no energy, no physical laws, then how could anything, let alone an entire universe, spontaneously arise from it? The philosophical principle of ex nihilo nihil fit, out of nothing, nothing comes, directly challenges the very notion of an uncaused beginning. Science, as an empirical discipline, fundamentally relies on observation and experimentation within the framework of existing physical laws. Its methods are designed to explore the relationships between phenomena within the universe. But the Big Bang's origin point represents the very boundary of this framework. It's the moment when the laws of physics, as we currently understand them, either came into being or underwent a radical transformation. Asking what caused the Big Bang is, in a very real sense, asking about something that existed outside the dominion of physics as we know it. It's akin to asking what is north of the North Pole. The question itself might be ill-posed within the conceptual map we use to navigate reality. This intellectual impasse has historically relegated the first cause question to the domains of theology and metaphysics, where concepts of divine creators or eternal, uncaused entities provided a resolution to the infinite regress of causality. If every cause must have a prior cause, then to avoid an endless, unsatisfying chain, there must ultimately be an unmoved mover, or an uncaused first cause that simply is. This philosophical argument, most famously articulated by Aristotle and later by Thomas Aquinas, posits a necessary being, a prime originator that doesn't require an external explanation because its existence is inherent. However, modern cosmology grapples with this ancient paradox from a distinctly scientific perspective, seeking explanations that remain within a naturalistic framework, even if that framework must be radically expanded. The goal is not to invoke a supernatural explanation, but to understand if there's a deeper, more fundamental set of physical laws or conditions that could inherently lead to the spontaneous emergence of a universe, thereby circumventing the need for an external creator in the conventional sense. This quest becomes an attempt to find a self-consistent, self-generating cosmic system, a universe that is, in some ultimate sense, its own cause. The first cause paradox forces scientists to reconsider the very nature of time. If time itself began with the Big Bang, then the question, what happened before the Big Bang, might be nonsensical. There would be no before in a temporal sense, only a conceptual boundary. This radical idea challenges our linear perception of time, suggesting it might be an emergent property of the universe rather than an eternal pre-existing dimension. If time is indeed born with the cosmos, then its origin cannot be an event in time, but rather the beginning of time, dissolving the causal chain into something entirely new. This pivotal question, therefore, isn't just an abstract intellectual exercise. It drives the most advanced and speculative research in theoretical physics and cosmology. It compels us to explore realms where space-time might be cyclical, where our universe is but one bubble in an infinite multiverse, or where the very laws of physics are not fundamental but emergent from a deeper, more intricate reality. Each proposed solution, from the oscillating universe to quantum fluctuations, attempts to reframe the concept of a beginning, seeking a mechanism that allows for the emergence of our cosmos without violating the principle of causality or resorting to an inexplicable, uncaused external agent. It pushes science to its absolute informational frontier, compelling us to imagine what lies beyond the observable and the currently conceivable. Having explored the profound implications of the first cause, paradox, we now turn our attention to the very heart of the Big Bang model's initial mystery, the singularity. This isn't just a speculative concept, it is the theoretical nexus, the point where our most robust scientific frameworks like general relativity lead us when extrapolated backward in time, only to abruptly break down. It represents the ultimate boundary of our current understanding, a cosmic veil beyond which the familiar laws of physics become utterly mute. Imagine, if you can, the entire observable universe compressed into a volume immeasurably smaller than a single atom. Within this infinitesimal speck, all the energy, matter and space-time that now stretch across billions of light-years were concentrated to an infinite density, an infinite temperature. This is the Big Bang singularity. It's crucial to understand that this wasn't an explosion into pre-existing space, but rather the explosive expansion of space itself, creating and defining its own geometry as it unfurled. At this point, the curvature of space-time would have been so extreme, so beyond any scale we can visualize, that the very fabric of reality as we perceive it ceases to hold meaning. The concept of a singularity is not unique to the Big Bang. Einstein's monumental theory of general relativity, which describes gravity as the curvature of space-time, also predicts singularities at the heart of black holes. There, matter collapses under its own immense gravity to an infinitely dense point, creating a region from which nothing, not even light, can escape. The Big Bang singularity, however, is a cosmological singularity, representing not merely the endpoint of a collapsing star but the initial condition of the entire cosmos. It is the beginning of everything, space, time, and the very fields that govern matter and energy. But herein lies the profound challenge. At the singularity, the equations of general relativity yield absurd, undefined results. Parameters like density, temperature, and space-time curvature surge to infinity, rendering any attempt to calculate or describe the conditions there impossible. It's a mathematical dead end, a signpost indicating that our current understanding of physics is incomplete. General relativity, a classical theory, beautifully describes gravity on large scales, dictating the dance of planets and galaxies. But it was never designed to operate in the quantum realm of the unimaginably small and energetic, where the Big Bang singularity resided. This is precisely where the two great pillars of 20th century physics, general relativity and quantum mechanics, come into irreconcilable conflict. Quantum mechanics, which governs the behavior of matter and energy at the atomic and subatomic levels, describes reality in terms of probabilities, discrete energy packets, and a fundamental fuzziness that stands in stark contrast to the smooth, deterministic curves of space-time envisioned by Einstein. At the Big Bang singularity, the universe was simultaneously immense in its energy content and infinitesimally small in its spatial extent. This confluence of extreme gravity and quantum effects means that neither theory alone can accurately describe the conditions. We're attempting to use a carpenter's hammer to perform microsurgery, or a microscopic probe to map a continent. Our tools are simply inadequate for the task at hand. The theoretical boundary where these two theories must merge is known as the Planck epoch, an incredibly brief interval lasting from time zero to approximately 10⁻43 seconds after the Big Bang. This Planck time is derived from fundamental physical constants, the speed of light, Planck's constant from quantum mechanics, and Newton's gravitational constant. It represents the smallest meaningful unit of time and, by extension, the smallest meaningful unit of length, Planck length. Below this scale, the very concepts of continuous space-time and causality begin to blur into a frothing quantum foam, a tumultuous, unpredictable realm where space and time themselves may not be fundamental, but emergent. The inability of our current physics to describe the singularity means that any information about what might have existed before it, or what mechanism initiated it, is effectively lost to us. It's like reaching the edge of a map that simply says, "Here be dragons," or trying to measure the precise temperature of a phenomenon that burns infinitely hot. The singularity acts as an informational firewall, preventing us from extrapolating backward through it with any confidence. We cannot simply run the cinematic reel of cosmic history in reverse and expect a coherent picture of the moments preceding the Big Bang. The film simply burns out at that critical juncture. This profound limitation is not a sign of scientific failure, but rather a powerful impetus for deeper inquiry. The Big Bang singularity is the siren call for a unified theory of quantum gravity, a single, overarching framework that can seamlessly reconcile general relativity and quantum mechanics. Such a theory would ideally describe gravity at all scales, from the smallest subatomic particles to the largest cosmic structures, and crucially, it would be able to model the extreme conditions of the early universe, including the singularity itself, without breaking down. The pursuit of quantum gravity has given rise to some of the most ambitious and speculative ideas in theoretical physics, notably string theory and loop quantum gravity. These approaches, each with their own elegant mathematics and profound implications, attempt to replace the problematic point-like singularity with something more physically plausible. String theory, for instance, postulates that fundamental particles are not point-like but rather tiny, vibrating strings, and that spacetime itself might have extra curled-up dimensions. In some string theory models, the Big Bang singularity could be smoothed out, or even replaced by a bounce from a previous cosmic era. Similarly, loop quantum gravity quantizes spacetime itself, suggesting that space is not continuous, but made of discrete, indivisible loops. In this framework, the singularity might be avoided as spacetime cannot be compressed beyond a certain Planck scale minimum, potentially leading to a quantum bounce, rather than an infinite collapse. The resolution of the singularity is thus not just an academic exercise, it is pivotal to answering the first cause paradox. If quantum gravity can describe a universe that doesn't begin with an infinite density, but rather a finite, albeit incredibly dense, state, a state that might have emerged from a prior cosmic phase or a deeper quantum reality, then the Big Bang ceases to be an uncaused event, and instead becomes a transition within a larger, self-consistent cosmic narrative. Until such a unified theory is empirically confirmed, however, the singularity remains a stark reminder that our understanding of the universe's ultimate genesis is profoundly incomplete, a scientific frontier that continues to beckon us into the unknown. The breakdown of physics at the singularity leaves us at a conceptual dead end, demanding a more complete picture of the universe's ultimate origin. One of the most compelling and ancient solutions to this impasse, predating even modern cosmology, is the idea of a cyclical cosmos, a universe that doesn't simply begin and end, but rather undergoes an endless series of births, deaths, and rebirths. This concept, often termed the oscillating universe, or, in its more modern iteration, the Big Bounce, posits that our Big Bang might not be the singular moment of creation, but merely one event in an eternal, self-perpetuating cosmic cycle. The classical vision of a cyclical universe emerged from early interpretations of general relativity, long before the discovery of dark energy. If the total gravitational pull of all matter in the universe was strong enough to eventually halt the cosmic expansion, the universe would reach a maximum size and then begin to contract. This contraction would accelerate, ultimately leading to a big crunch, a reverse of the Big Bang, where all matter and energy collapse back into an infinitely dense, hot state. The oscillating model then envisioned this big crunch as instantaneously transitioning into a new Big Bang, restarting the cycle. This offered an elegant solution to the first cause paradox. The universe simply is, without a true beginning or end, forever regenerating itself. However, a significant challenge quickly emerged for this simple oscillating model: the problem of entropy. Entropy, often understood as a measure of disorder or randomness, is a fundamental thermodynamic quantity that, according to the second law of thermodynamics, can only ever increase in a closed system. Each cycle of a simple Big Crunch Big Bang universe would, inevitably, accumulate more entropy. This means successive cycles would be longer, larger, and dilute their energy more widely, preventing them from returning to the exact initial conditions. Over an infinite number of cycles, this inescapable increase in entropy would imply that the universe should have already reached a state of maximum disorder, a heat death, or that the cycles must have had a finite beginning after all. A perpetually oscillating universe, governed by classical physics, would be like a spring that slowly loses its tension with each rebound, eventually failing to bounce at all. This thermodynamic hurdle largely led to the abandonment of the simple oscillating model in the late 20th century. Furthermore, observations from the late 1990s dramatically altered our understanding of the universe's fate. The discovery of dark energy. This mysterious force is now understood to be driving the accelerated expansion of the universe. Current data strongly suggest that the universe will not contract in a big crunch. Instead, it will continue to expand indefinitely, eventually leading to a cold, empty, big freeze, or heat death, as galaxies drift apart and stars burn out. This cosmic forecast seemed to definitively rule out a cyclical universe model for our particular cosmic epoch. Yet, the allure of a universe without a beginning or end persisted, compelling theorists to develop more sophisticated models that could circumvent the entropy problem and incorporate modern cosmological understanding. This gave rise to the Big Bounce theories, which differ from their classical predecessors by employing concepts from quantum gravity to avoid the problematic singularity and potentially reset entropy. One prominent approach stems from loop quantum gravity, LQG, a theoretical framework that attempts to quantize spacetime itself. In LQG, space is not a smooth continuum, but is instead composed of discrete, indivisible loops, or quanta. This means there's a minimum possible size for spacetime, preventing infinite compression. Instead of collapsing into a singularity, an earlier universe, as it contracts, would reach a state of incredibly high but finite density, where quantum gravitational repulsive forces would overwhelm gravity and cause it to bounce back into expansion. This quantum bounce would effectively smooth out the singularity, replacing it with a transition point where an earlier contracting phase gives way to our current expanding phase. In this scenario, our Big Bang is not an absolute beginning, but merely the aftermath of a cosmic rebound. Another set of Big Bounce models arises from string theory and its extension, brain cosmology. In these highly speculative frameworks, our four-dimensional universe, three spatial, one temporal, is seen as a brain existing within a higher dimensional bulk space. The Big Bang, in some brain models, is not the result of a singularity, but the consequence of two or more such brains colliding or interacting. Imagine two enormous parallel membranes slowly drifting through a higher dimension. When they eventually collide, the immense energy released could manifest as a Big Bang, triggering a new epoch of expansion. After their interaction, the brains might separate again, only to drift back together for another collision, creating an eternal cycle of cosmic creation and destruction. The ekpyrotic universe model, for example, posits such a collision as the origin of our Big Bang, potentially offering a mechanism for the universe to be born anew without inheriting the entropy of a previous cycle, or even having entropy effectively reset between phases. The challenge of entropy in these modern Big Bounce models is addressed through various mechanisms. Some propose that the very act of bouncing or colliding could dissipate or dilute entropy, preventing its accumulation across cycles. Others suggest that the reset occurs through a phase transition in the fundamental laws of physics or the nature of spacetime itself during the extreme conditions of the bounce. if the universe's fundamental constants or the dynamics of its expansion are somehow recalibrated with each cycle, the entropy problem might be circumvented. This is a subtle but crucial distinction. These aren't simple oscillations, but sophisticated transformations that allow for a continuous, yet ever-evolving cosmic narrative. While observationally challenging, scientists are actively searching for potential signatures of a big bounce. For instance, some models predict specific patterns in the cosmic microwave background radiation, such as subtle deviations from the standard inflationary predictions, or the presence of specific types of primordial gravitational waves that could be remnants of the pre-bounce contracting phase. The detection of such patterns would provide tantalizing, albeit indirect, evidence that our universe might have an ancestry extending beyond the Big Bang. Furthermore, the role of dark energy remains critical. If dark energy were to eventually weaken or reverse its repulsive effect, a future Big Crunch might still be possible, reigniting the interest in these cyclical scenarios. The philosophical implications of a cyclical cosmos are profound. It shifts the question from what caused the Big Bang to what causes the cycle, or what initiated the first cycle. In essence, it redefines the concept of a cosmic beginning, replacing a singular, inexplicable genesis with an eternal process. The universe becomes a self-organizing, self-renewing entity, a grand cosmic engine that perpetually remakes itself. This framework allows for a universe that is truly eternal, without ever requiring an external creator or an uncaused first cause in the traditional sense, as causality would simply extend backward indefinitely through prior cycles. However, it still leaves a subtle, nagging question. What set up the rules for this eternal oscillation? Is the cycle itself an uncaused phenomenon, or is there a deeper, underlying reality that dictates its eternal rhythm? The cyclical universe, while providing elegant answers, often merely pushes the ultimate question of origin to a higher, more abstract level of existence. The breakdown of our physics at the Big Bang singularity, as we've discussed, is a profound limitation. But what if the very mechanism that resolved some of the Big Bang's earliest puzzles also offered a radical new perspective on its origin, hinting that our universe is merely one among an infinite ensemble? This brings us to the revolutionary concept of cosmic inflation, and its mind-bending implication, the multiverse. Cosmic inflation, first proposed in the early 1980s by physicists like Alan Guth, is an extension to the standard Big Bang model, not a replacement. It postulates that in the first fleeting fraction of a second after the Big Bang, perhaps from 10 raw or 36 to 10 raw or 32 seconds, the universe underwent an extraordinary period of exponential expansion. During this incredibly brief epoch, space-time expanded at a rate so immense that its size increased by a factor of at least 1026, transforming a microscopic quantum fluctuation into a macroscopic patch of space-time that would eventually become our observable universe. To understand this, imagine a tiny fundamental field permeating the very early universe, dubbed the inflaton field. This field possessed an immense amount of potential energy, analogous to a ball perched atop a very high flat plateau. As the universe began, this inflaton field was rolling slowly down this plateau. During this slow roll, its potential energy acted like a cosmological constant, generating a repulsive gravitational force that drove the incredibly rapid, exponential expansion of space. This isn't like an explosion of matter into space. It's an explosion of space itself, stretching distances between points faster than the speed of light, while never violating Einstein's local speed limit for objects within space. Eventually, the inflaton field fell into a lower energy state, much like the ball rolling off the plateau into a valley. As it settled, its energy was released and converted into a hot, dense plasma of particles and radiation, the primordial soup from which all the matter and energy of our universe would eventually condense. This energy release marks the reheating phase, effectively the onset of the traditional Big Bang era as we understand it, where the universe began its more gradual expansion and cooling. So in this view, inflation is the prelude to the Big Bang, setting the stage and providing the initial conditions for our cosmos. Inflation successfully resolves several key problems within the standard Big Bang model that were otherwise intractable. For instance, the flatness problem asks why the universe's geometry is so incredibly close to being flat. a specific curvature that is highly improbable unless fine-tuned. Inflation stretches any initial curvature so dramatically that it effectively flattens the universe, much like blowing up a small wrinkled balloon to an enormous size makes its surface appear smooth. Secondly, the horizon problem questions why the cosmic microwave background (CMB) radiation, observed across vast, causally disconnected regions of the sky, exhibits an almost perfectly uniform temperature. Inflation solves this by positing that these regions were once causally connected in a tiny, pre-inflationary patch, allowing them to reach thermal equilibrium before being stretched far apart by the rapid expansion. However, the very nature of quantum mechanics combined with the dynamics of the inflaton field leads to a profound and highly speculative extension of the inflationary paradigm, eternal inflation. In many inflationary models, the inflaton field doesn't decay uniformly everywhere. Instead, quantum fluctuations, the inherent jitteriness of reality at its smallest scales, can cause different regions of the inflating spacetime to behave differently. In some patches, the inflaton field might successfully decay, ending inflation and giving birth to a bubble universe like our own. But in other regions, quantum fluctuations can locally reignite or sustain inflation, causing those patches to continue expanding exponentially. This leads to a self-perpetuating fractal process where inflation never truly ends globally. Instead, it continuously spawns new bubble universes, each of which has its own localized Big Bang event. Imagine an endlessly expanding foam, where some bubbles stabilize and mature, while the foam itself continues to generate new bubbles ad infinitum. Our observable universe, with its 13.8 billion-year history, would simply be one such bubble, one localized pocket of space-time where inflation ended and the traditional Big Bang began. This eternal inflation scenario provides a scientific pathway to the concept of a level 2 multiverse, as categorized by physicist Max Tegmark. In this multiverse, an infinite number of these causally disconnected bubble universes exist, each having potentially different physical constants, particle masses, and even different numbers of spatial dimensions. The laws of physics that govern our universe, the strength of gravity, the charge of an electron, the speed of light, could be mere local manifestations within our bubble, while other bubbles operate under entirely different rule sets, some hospitable to life, others barren beyond imagination. The implications for the first cause paradox are staggering. If eternal inflation is correct, then our Big Bang is not the absolute beginning of everything, but rather a beginning within a larger, eternally generating meta-universe. The origin question is then shifted from what caused our Big Bang to what caused the eternal inflation, or the laws that govern its perpetual bubbling. While it pushes the problem further back, it offers a framework where the initial conditions of your universe don't require external creation, but emerge from a larger, self-consistent cosmic process that has no ultimate beginning or end. This view also offers a compelling, albeit controversial explanation for the apparent fine-tuning of our universe. The constants of nature in our universe seem exquisitely balanced for the existence of life. If even slightly different, stars wouldn't form, atoms wouldn't bind, and life as we know it would be impossible. In a single universe model, this fine-tuning often leads to arguments for a conscious designer. However, in an eternal inflation multiverse, the existence of an infinite number of universes with varying constants makes it statistically inevitable that at least some, like ours, would possess the precise conditions necessary for observers to arise. We simply find ourselves in one of the universes where our existence is possible, an anthropic selection effect. Despite its explanatory power and elegant resolution of certain cosmological puzzles, the concept of eternal inflation and the multiverse remains highly speculative. It is notoriously difficult, if not impossible with current technology, to gather direct observational evidence for other bubble universes. Scientists are exploring potential, indirect signatures, such as subtle patterns in the cosmic microwave background that might be left by a collision with another bubble, or anomalies in the large-scale structure of our universe. However, these remain firmly in the realm of theoretical prediction. Ultimately, while the theory of eternal inflation beautifully addresses the paradox of our Big Bang, by situating it within a grander, self-perpetuating cosmic landscape, it doesn't entirely eliminate the first cause question, it merely elevates it to a higher plane. What created the inflaton field? What governed its initial state? What are the fundamental meta-laws that allow for eternal inflation to occur? The multiverse, while offering a breathtaking expansion of reality, still compels us to ask, what lies beneath the bubbling foam? What primordial engine drives the ceaseless creation of universes? Even the breathtaking expanse of the multiverse, with its infinite cosmic bubbles, still leaves a lingering question. What ultimate principle or meta-law governs the eternal inflation that spawns them? What, if anything, exists before the bubbling foam or the quantum fields that drive its ceaseless generation? This leads us to one of the most radical and counterintuitive propositions in theoretical physics, the idea that the universe, or perhaps the multiverse itself, could have spontaneously emerged from what is often loosely termed nothingness, a concept deeply rooted in the perplexing realm of quantum mechanics. To truly grapple with this idea, we must first redefine nothing. In classical physics, a vacuum is empty space, a void, but in quantum mechanics, the vacuum is anything but empty. It is a seething, effervescent sea of activity, a quantum foam perpetually bubbling with virtual particles that wink into and out of existence in incredibly short timescales. This isn't philosophical nothingness, it's a dynamic, energetic state governed by the fundamental laws of quantum physics, a realm of potentiality. According to the Heisenberg uncertainty principle, there's an inherent fuzziness to reality, meaning that over very short durations, energy and matter can spontaneously appear as long as they vanish quickly enough to satisfy the principle's constraints. It's like borrowing money from the bank. You can have a large sum for a moment, provided you pay it back immediately. Now, extend this principle to the very fabric of spacetime itself. What if an entire universe could borrow enough energy from this quantum vacuum, not just for a fleeting moment, but for long enough to initiate a sustained existence? This is the core concept behind models of spontaneous creation, where our universe effectively tunnels into existence from a pre-geometric quantum state. In these highly speculative scenarios, the Big Bang isn't an explosion of pre-existing matter, nor a bounce from a prior universe, nor a collision of brains. Instead, it is the manifestation of a colossal quantum fluctuation, a cosmic bubble inflating into being from the inherent instability and potential energy of the quantum vacuum. One of the most profound theoretical frameworks attempting to describe such a genesis is the no-boundary proposal, put forth by Stephen Hawking and James Hartle. Their model suggests that the universe has no initial singularity, no sharply defined beginning point in time. Instead, it proposes that the universe, at its earliest moments, was finite in extent but had no boundary, much like the surface of a sphere has a finite area but no edge. In this framework, time itself emerges from a timeless or imaginary time state, making fundamentally meaningless, as there was no before in the temporal sense. The universe, in a sense, simply is, without a sharp, causally problematic beginning. It's a self-contained entity, a universe that creates itself from its own inherent quantum properties without needing an external cause. This concept radically reinterprets the first cause paradox. If the fundamental laws of quantum mechanics allow for the spontaneous emergence of a universe from a state that, for all intents and purposes, looks like nothingness in a classical sense, then the universe itself could be a self-creating entity. The laws of physics become the ultimate creator, not an external agent, but the inherent rules that govern existence even in its most nascent, pre-spatial, pre-temporal forms. The question then shifts from who or what caused the Big Bang to why are there quantum laws that permit such spontaneous creation? The laws themselves become the uncaused first cause, or perhaps they are self-consistent and require no external justification. Furthermore, many of these spontaneous creation models are naturally linked with cosmic inflation. A universe that tunnels into existence from the quantum vacuum would likely do so in a state of high energy density, perfectly primed for the rapid expansion of inflation. This inflationary phase would then smooth out any initial irregularities and expand the nascent universe to the vast scales we observe before transitioning into the standard Big Bang hot phase. So, quantum tunneling could be the ultimate spark that ignites the inflaton field, thus providing the very initial conditions for the Big Bang and subsequent cosmic evolution. Consider the sheer scale shift implied here. the microscopic probabilistic whims of quantum particles, typically confined to the subatomic realm, are extrapolated to the grandest possible scale, giving birth to entire cosmos. It's a breathtaking leap, suggesting that the same fundamental principles that govern the jittery dance of electrons in an atom might also be responsible for the genesis of galaxies and the sprawling cosmic web. This perspective posits a universe where creation is not an anomalous event, but an inherent, albeit rare, possibility within the quantum realm. However, these ideas reside firmly at the frontier of theoretical physics, far beyond the reach of direct empirical verification with current technologies. The conditions required to test such hypotheses existed only in the universe's earliest, most extreme moments, making observation incredibly challenging. The very notion of quantum gravity, which is essential for these models, is itself still a work in progress, with competing theories like string theory and loop quantum gravity offering different mathematical descriptions of how gravity behaves at the Planck scale. Until a comprehensive and experimentally verifiable theory of quantum gravity emerges, these scenarios, while intellectually compelling, remain elegant mathematical possibilities rather than established scientific fact. The philosophical implications are profound. If the universe can emerge from a quantum vacuum without an external cause, it fundamentally redefines our understanding of creation and existence. It suggests a cosmos that is inherently self-sufficient, a grand, self-organizing system that doesn't need a push from outside its own intrinsic laws. But even this nothingness is not truly empty. It is a substrate of quantum fields and potentials. The ultimate question then becomes, where did these fundamental quantum laws themselves come from? Are they eternal, inherent truths of existence? Or are they, too, emergent from an even deeper, more abstract reality? Spontaneous creation, from quantum foam, while seemingly providing an answer, often leads us to yet another layer of cosmic mystery, challenging us to consider the nature of laws themselves. We have ventured into the quantum foam, where universes might spontaneously emerge, driven by the inherent probabilistic nature of reality itself. Yet, this still leaves us with a fundamental question. What dictates the rules by which this quantum foam behaves, or by which brains collide, or indeed, by which any cosmic cycle perpetuates? This brings us to a more abstract yet profoundly important realm of inquiry. The possibility of higher-order physical laws, a deeper, more fundamental set of principles that govern not just our universe, but the very creation and evolution of reality itself. To clarify, when we speak of physical laws in our universe, we typically refer to the standard model of particle physics and general relativity. These are the mathematical descriptions that govern the forces, particles, and spacetime within our cosmos. They dictate everything from the strong nuclear force binding quarks into protons, to the electromagnetic force governing light, to the gravitational pull that shapes galaxies. These laws are characterized by specific constants, like the gravitational constant, the speed of light, and the masses of fundamental particles, values that appear to be fixed and universal throughout our observable universe. But the first cause paradox prompts us to ask, where did these specific laws and constants come from? Why these rules and not others? Why is gravity precisely this strong, or the electron's charge exactly this value? The very possibility of cyclical universes, or the multiverse, or spontaneous creation from quantum foam, implicitly relies on a set of underlying principles that permit such phenomena. Could these underlying principles be considered higher-order physical laws, a meta-framework that determines the characteristics of entire universes? Imagine a vast cosmic operating system. Our universe, with its specific physical laws and constants, would be like a particular program running on this system. The higher-order laws would be the fundamental code of the operating system itself, the rules that allow different programs, universes, to be created, run, and interact. These laws would not exist within our spacetime, but would be more fundamental, existing at a level above or outside it, dictating the very conditions for existence across potentially infinite realities. One way to conceptualize these higher-order laws is through the lens of mathematical elegance and self-consistency. Many physicists believe that the ultimate theory of everything, a grand unified theory, will be characterized by profound mathematical beauty and internal coherence. If such a theory exists, it might be so robust and self-contained that it must exist. Or rather, It is the only logically consistent way for reality to be structured. In this view, the higher-order laws are not arbitrary, but are necessary mathematical truths from which all possible universes and their specific laws emerge. Our universe, then, would simply be one of the mathematically permissible expressions of these deeper principles. The concept of a multiverse, especially one arising from eternal inflation, naturally lends itself to the idea of higher-order laws. If different bubble universes possess different physical constants and even different dimensions, then there must be some overarching mechanism, some higher-order law, that governs this variation. It's not simply random. There must be a distribution, a probability landscape, or a set of meta-rules that determine which universes are possible and how their parameters are set. These higher-order laws would be the generator of universes, defining the space of all possible realities. Some theories, particularly those rooted in string theory, hint at such a deeper structure. String theory, with its 10 or 11 dimensions, suggests that the curling up of extra dimensions, a process called compactification, could determine the specific physical constants and forces we observe in our four-dimensional universe. There are potentially an astronomical number of ways these extra dimensions can compactify, each leading to a different set of physical laws. This vast landscape of possibilities, often referred to as the string theory landscape, implies a higher-order law that governs the geometry and topology of these extra dimensions, thereby indirectly determining the laws of physics in the resulting universes. The Big Bang in this context would be the emergence of a specific compactification pattern from a more fundamental, higher-dimensional reality. The search for higher-order laws is also intertwined with the very nature of information and computation. Some speculative theories propose that reality itself is fundamentally informational or computational. In this digital universe hypothesis, the ultimate reality is not matter or energy, but bits of information, and the laws of physics are akin to algorithms or programs. If this is the case, then higher-order laws would be the meta-algorithms that define the rules for processing this information, allowing complex emergent phenomena, including entire universes, to arise. This would suggest a universe that is self-referential, perhaps even self-simulating, where causality and creation are intrinsic to its informational structure. The challenge, of course, is that these higher-order laws are, by definition, beyond our direct observational reach. We are inhabitants of our universe, bound by its laws and dimensions. Detecting or inferring laws that govern the creation of universes requires an unprecedented leap in theoretical understanding and potentially new forms of empirical evidence, perhaps subtle patterns in our own cosmos that could only arise from such a meta-framework. For instance, deviations from expected cosmological parameters or anomalies in fundamental constants could hint at a deeper, underlying physical structure. Philosophically, this concept pushes the first cause even further into abstraction. If the Big Bang is caused by higher-order laws, then the question becomes what caused those laws? Are they eternal, inherent, and self-existent mathematical truths? Or could they, too, be emergent from an even deeper, more primal layer of reality, a perpetually nesting doll of fundamental principles? The pursuit of higher-order laws represents humanity's attempt to find the most fundamental, irreducible explanation for existence, to discover the ultimate why that requires no further explanation, because it is the explanation. It's a quest for cosmic self-consistency, a universe whose rules are so elegant and unavoidable that they are, in a profound sense, their own origin. Having delved into higher-order physical laws that might govern the very creation of universes, we are led to an astonishing observation about our own cosmos, its seemingly improbable suitability for the emergence of life. This is the fine-tuning problem, a profound puzzle that challenges our assumptions about cosmic randomness and provides a powerful, if controversial, lens through which to view the Big Bang's origin. It asks, is the universe's capacity for life a cosmic accident, a fortunate roll of the dice, or is there a deeper reason for its apparent precision? The fine-tuning problem emerges from the values of fundamental physical constants and the initial conditions of the universe. Consider the gravitational constant, the strength of the electromagnetic force, the masses of elementary particles, or the ratio of dark energy to matter. These are not arbitrary numbers. They are the bedrock parameters that define the universe's behavior. Scientists have calculated that even minute deviations in these values, often less than a few parts in a million or even a trillion, would lead to a radically different cosmos, one utterly inhospitable to the formation of stars, galaxies, or complex chemistry, let alone life. For example, if the strong nuclear force which binds protons and neutrons together in atomic nuclei were just slightly weaker, stable atomic nuclei beyond hydrogen couldn't form, and stars wouldn't ignite. If it were slightly stronger, hydrogen would fuse too readily, consuming all the universe's protons early on, or creating too much helium, preventing the formation of water. Similarly, if the electromagnetic force were marginally stronger or weaker, electrons wouldn't orbit nuclei stably, or chemical bonds, the very basis of molecular complexity and life, would be impossible. The universe would be a desolate expanse of unbonded particles. The initial conditions of the universe are equally critical. The smoothness and uniformity of the early universe, as evidenced by the cosmic microwave background, are breathtaking. Yet, it also contained tiny density fluctuations, the seeds for galaxies. If these fluctuations had been too small, gravity would never have been able to overcome the expansion, and no stars or galaxies would have formed. The universe would be a diffuse, featureless gas. If they had been too large, the universe would have collapsed back on itself too quickly, or formed only black holes, leaving no stable environments for planets. The balance is astonishingly precise, creating a universe that is just right for complexity to emerge over billions of years. The discovery of dark energy further amplified this puzzle. The cosmological constant representing dark energy is an incredibly small yet positive value. If it were even slightly larger, its repulsive force would have caused the universe to expand so rapidly that matter would have dispersed before gravity could pull it together to form galaxies and stars. The universe would be a rapidly expanding empty void. If it were much smaller, or negative, the universe might have collapsed too soon. The measured value of dark energy is so infinitesimally small compared to what theoretical physics might generically predict that it is often called the cosmological constant problem, a discrepancy of 120 orders of magnitude, the largest mismatch between theory and observation in all of science. Its existence and its precise value appear to be extraordinarily fine-tuned. So, how do scientists grapple with this apparent cosmic precision? There are broadly two scientific categories of explanation, each with profound implications for the Big Bang's origin. The first is the brute fact explanation. It's simply a coincidence. The universe happens to have these values, and we, as observers, simply find ourselves in a universe where these conditions allow for our existence. This is sometimes referred to as the weak anthropic principle. The conditions we observe must be consistent with our own existence as observers. While scientifically sound in its observation, it is often seen as intellectually unsatisfying by many, as it offers no deeper explanation for why the universe is this way. It essentially says, that's just how it is. The second, a more widely discussed scientific explanation, particularly in the context of the Big Bang's origin, leans heavily on the concept of the multiverse, which we explored in the previous section. If our universe is just one of an infinite ensemble of universes, each with its own random set of physical laws and constants, as predicted by eternal inflation or string theory's landscape, then it becomes statistically inevitable that at least some universes would possess the precise conditions necessary for life to emerge. We simply happen to inhabit one of those rare, life-permitting universes. It's akin to winning a cosmic lottery. If there are infinite tickets, someone is bound to win the jackpot. This strong anthropic principle argues that the universe must have the properties allowing for life, because if it didn't, we wouldn't be here to observe it. In this view, the fine-tuning isn't a miraculous precision, but a simple consequence of observer selection within a vast landscape of possibilities. The multiverse explanation offers an elegant way to resolve the fine-tuning problem without invoking supernatural intervention. It transforms what appears to be an astronomically improbable coincidence into a statistical certainty. However, as noted before, the multiverse itself is currently beyond direct empirical verification, and it raises its own set of first cause questions about the meta-laws that govern the generation of these many universes. Another, less common scientific approach proposes that the fundamental constants are not truly constant, but emergent properties that are determined by deeper, unknown physics, or that they evolve over cosmic time. If the constants are actually dynamic, perhaps they settled into their life-permitting values through some self-organizing principle of the universe, or perhaps they vary across different regions of a single, vastly larger universe. While some observations place tight constraints on the variability of these constants over cosmic time, the idea that they might emerge from a deeper underlying physics remains an active area of theoretical investigation. The fine-tuning problem therefore serves as a powerful intellectual bridge between the scientific and philosophical dimensions of the Big Bang's origin. It forces us to confront the deepest questions about the nature of reality and our place within it. Is the universe a random occurrence, a cosmic accident, or is there an underlying principle, perhaps encoded in higher-order laws, or realized through a multiverse, that makes existence, and indeed life, a natural outcome? The very fact that we can ponder such questions is, in itself, a testament to the extraordinary conditions that unfolded from the Big Bang, conditions that seem almost deliberately crafted for cosmic complexity and consciousness to arise. This profound cosmic coincidence continues to be one of the most compelling arguments for exploring what, or who, lies beyond the initial spark of our universe. Our journey through the speculative landscapes of cosmic origins, from the self-perpetuating cycles of the Big Bounce to the infinite expanse of the multiverse and the enigmatic depths of quantum foam, all ultimately converge on a singular, profound realization. The question of what caused the Big Bang pushes us to the absolute frontier of empirical science. Beyond the observable, beyond the reach of even our most advanced instruments, lies a realm where our methods of investigation begin to blur, and the very definition of scientific proof undergoes a radical transformation. To understand this limit, we must first grasp the concept of the observable universe. We can only perceive the part of the cosmos from which light, or any other form of information, has had time to reach us since the Big Bang. This defines our cosmic horizon, an expanding sphere centered on us. The most ancient light we can detect is the cosmic microwave background, CMB, the afterglow of the universe's recombination period, approximately 380,000 years after the Big Bang. Peering further back in time than the CMB is fundamentally impossible with light, because before that epoch, the universe was an opaque plasma, trapping photons like fog. This cosmic barrier means we can never directly see the singularity, or the Planck epoch, or any events that transpired in the fractions of a second immediately following time zero. It's like trying to see the origin of a fire by looking at its smoke. The source itself is obscured by the very process it initiated. This observational constraint is one layer of the frontier. The other, perhaps more challenging layer is the theoretical limitation. As we've discussed, the equations of general relativity, our bedrock theory of gravity and spacetime, break down at the singularity. They yield infinities, signaling that the theory itself is incomplete in such extreme conditions. To truly understand the Big Bang's earliest moments, we require a theory of quantum gravity, a unified framework that can reconcile Einstein's macroscopic view of gravity with the probabilistic discrete nature of quantum mechanics. Without such a theory, any descriptions of the Big Bang's ultimate cause remain speculative, resting on mathematical constructs that lack full empirical validation. This is not to say that science abandons the quest. Instead, it adapts its methods. When direct observation is impossible, theoretical physics steps in, building models based on logical consistency, mathematical elegance, and the ability to explain existing phenomena, even if they can only offer indirect or potentially untestable predictions about the ultimate origin. For instance, the inflationary paradigm, while lacking direct evidence for the inflaton field itself, is widely accepted because it elegantly resolves problems within the standard Big Bang model, like the horizon and flatness problems, and its predictions for the CMB's patterns align remarkably well with observations. But when inflation is extended to eternal inflation, leading to the multiverse, the empirical challenge escalates dramatically. How do we test for the existence of other universes causally disconnected from our own? The evidence for ideas like cyclical universes often comes in the form of mathematical consistency, internal coherence, and philosophical attractiveness. A theory that posits a self-generating universe, for example, might be favoured for its elegance in addressing the first cause paradox without resorting to external or supernatural explanations. Some models might predict subtle, unique signatures in the CMB or in the distribution of matter that future observatories might detect. For example, specific patterns of gravitational waves from the very early universe could be relics of a quantum bounce or a collision with another brane. However, these are often at the very edge of detectability, pushing the limits of our technological prowess. The distinction between observable and unobservable phenomena becomes critical here. We can observe galaxies billions of light years away, remnants of early cosmic structure. We can analyze the precise fluctuations in the CMB. These are empirical facts. But the mechanism that sparked the Big Bang itself, the before the very concept of time, remains shrouded potentially forever beyond our direct empirical gaze. This is where scientific inquiry must acknowledge its boundaries and humbly admit that some questions, while deeply scientific in their formulation, may transcend the very tools designed to answer them. This frontier is where science intersects most profoundly with philosophy. While science seeks to explain how the universe operates, the question of ultimate origin touches upon the deeper why. It compels us to ask if the universe is inherently understandable in its entirety through natural laws, or if there are aspects that simply are, without needing a preceding cause. It challenges the assumption that every question must have an answer derivable through empirical means. Perhaps the universe's beginning is not a singular event in time, but the very genesis of time itself, rendering any before meaningless. The current epoch of cosmology is therefore one of immense intellectual excitement, but also profound humility. We're using theoretical scaffolding to build bridges over chasms of ignorance, trying to glimpse a reality that may be fundamentally unseeable. The pursuit of quantum gravity, the ongoing search for anomalies in the CMB, and the development of new mathematical models are all attempts to push this frontier back, to convert the currently unobservable into the indirectly inferable. But until that breakthrough arrives, the ultimate creator of the Big Bang, or the ultimate mechanism behind it, remains a testament to the fact that even the most powerful scientific enterprise eventually confronts the limits of its own empirical reach, leaving us to ponder the deepest mysteries at the very edge of existence. We have meticulously traversed the most ambitious frontiers of cosmological thought, exploring the cyclical dance of big bounces, the endless self-generation of the multiverse, the spontaneous emergence from quantum foam, and the elusive dictates of higher-order laws. Each theoretical construct offers a tantalizing pathway to address the first cause paradox, pushing the boundaries of what we conceive as possible. Yet, as we withdraw from these speculative realms, we are consistently drawn back to a profound, humbling realization. Despite humanity's unparalleled intellectual drive, the ultimate genesis of the Big Bang remains an enduring enigma, a point where empirical science, for now, meets the seemingly unknowable. The confrontation with the unknowable is not a failure of science, but rather a testament to its rigor. It is the recognition of a boundary, a conceptual horizon beyond which our current methodologies and observational tools cannot penetrate. We are creatures intrinsically bound by spacetime and causality, dimensions and principles that themselves appear to have been born with the Big Bang. To ask what happened before the Big Bang, or what created the conditions for it, is to grapple with concepts that may lie outside the very framework of time and space we inhabit and employ for understanding. It's like asking for a colour that exists beyond the electromagnetic spectrum. The question itself presupposes a reality that may not apply. Our most powerful scientific theories, general relativity and quantum mechanics, serve as our cosmic compass and map. General relativity describes the grand, sweeping curves of spacetime and the immense gravitational forces that shape the universe, but it collapses into meaningless infinities at the extreme densities of the Big Bang singularity. Quantum mechanics, conversely, governs the probabilistic, fuzzy realm of the infinitesimally small, where particles wink into and out of existence, but its principles struggle to describe gravity on cosmic scales. The unification of these two pillars into a theory of quantum gravity remains the holy grail of theoretical physics, precisely because it is needed, potentially smoothing out the singularity and offering a more coherent picture of ultimate origins. Until such a unified theory is empirically validated, our understanding remains fragmented at the crucial juncture. Even if a complete theory of quantum gravity were to emerge, it might not provide a definitive cause in the conventional sense. Instead, it might describe a self-consistent, mathematically elegant process where the universe, or a larger meta-universe, simply is without an external instigator. For instance, a universe arising from quantum foam might be an inherent spontaneous possibility within the laws of physics themselves, much like a particle spontaneously appearing in a vacuum. The laws then become the ultimate uncaused cause, a self-referential system that dictates its own emergence. This shifts the question from what created the universe to why these specific self-creating laws exist. This brings us to an epistemological limit. Can we ever truly step outside our universe, or the meta-laws that govern it, to understand its fundamental origins? Our capacity for knowledge is shaped by the very reality we seek to comprehend. Any scientific explanation, no matter how profound, must ultimately rely on some foundational assumptions: the existence of mathematical laws, the coherence of logic, the very possibility of physical processes. The first cause paradox at its deepest level questions whether there is an ultimate, irreducible foundation, or if reality is an infinite regress of explanations, or perhaps self-existent without needing a why. The enduring enigma therefore illuminates the profound difference between a scientific explanation and a philosophical one. Science aims to describe the mechanisms and processes of the natural world, testing hypotheses against observable evidence. When that evidence ceases, or when the mechanisms themselves become the object of inquiry, science pushes its theoretical boundaries, seeking consistency and predictive power, even if direct empirical proof is elusive. Philosophy, on the other hand, grapples with the underlying meaning, the implications for existence, and the limits of knowledge itself. It asks whether certain questions might be fundamentally unanswerable within any conceivable framework, or if the very nature of ultimate reality transcends our current conceptual tools. This constant interplay between the knowable and the unknowable fuels the engine of scientific discovery. The very discomfort of the unanswered spurs innovation, driving physicists to devise ever more sophisticated experiments and mathematicians to construct ever more elegant theories. The search for primordial gravitational waves, the meticulous analysis of the cosmic microwave background, and the quest for dark matter particles are all indirect attempts to gather faint echoes from the Big Bang's genesis, hoping for a clue that might unlock the ultimate secret. Each new observation, each theoretical refinement, however small, edges us closer to understanding the universe's initial conditions, even if the absolute before remains elusive. The creator of the Big Bang might not be a singular entity or event, but rather an intricate symphony of fundamental physical laws, quantum probabilities, and perhaps even higher dimensional dynamics that collectively weave the fabric of reality. It might be a universe that, in a profound sense, creates itself, not from nothing, but from the inherent potential encoded within the most fundamental principles of existence. This enduring enigma compels us to embrace the vastness of the unknown, reminding us that the cosmos holds secrets far grander and more intricate than our current imaginations can fully grasp. It is in this humbling confrontation with the limit of knowledge that the true awe and wonder of our universe are revealed, leaving us to forever ponder the magnificent question of where everything truly began. We have journeyed through the most ambitious frontiers of cosmological thought, tracing humanity's relentless quest to understand the ultimate genesis of our universe, from the elegant self-perpetuating dance of Big Bounce theories, where cosmic epochs succeed one another in an eternal rhythm, to the mind-bending expanse of the multiverse, where our Big Bang is but one in an infinite cascade of births, and into the strange frothing quantum foam from which entire realities might spontaneously emerge. We have explored the radical proposals of modern physics. We have even contemplated the existence of higher-order laws, a meta-framework dictating the very conditions for creation across unimaginable scales of existence. Each theory, a testament to human ingenuity and intellectual courage, attempts to push back the veil, to peer into the primordial darkness preceding our cosmic dawn. Yet despite these profound intellectual expeditions, the central question, the ancient first cause paradox that haunted philosophers millennia ago, remains. What or who sparked the Big Bang? Where did the fundamental laws, the initial conditions, or the very quantum potential for existence truly originate? The scientific answers we have explored while offering elegant resolutions to various puzzles within the cosmic narrative, often elevate the ultimate question to a higher plane of abstraction rather than dissolving it entirely. If the universe bounces, what initiated the first bounce? If the multiverse endlessly bubbles, what governs the meta-laws of that infinite creation? If reality emerges from quantum foam, what dictates the inherent properties of that foam? This unwavering persistence of the first cause paradox is not a mark of scientific failure, but rather a profound indicator of reaching the absolute limits of current empirical science and, perhaps, the very boundaries of human comprehension itself. Our understanding of causality is inherently linear, forged in a universe where events unfold sequentially in time. But if time itself, as many cosmologists suggest, began with the Big Bang, then the concept of before loses its very meaning. To ask what came before the genesis of time is like asking for a direction beyond north at the North Pole. The question, within our established conceptual map, becomes ill-posed. This forces a radical re-evaluation of how we frame the problem, moving beyond simple temporal succession to consider a reality where existence might be fundamentally self-contained, self-referential, or eternal in a way that transcends our linear understanding. The Big Bang singularity, where our most cherished equations of general relativity break down, stands as a stark monument to this limit. It is the point where the universe was compressed into an unimaginably dense, hot state, a realm where quantum effects and extreme gravity merge, demanding a unified theory of quantum gravity that currently eludes us. Without this overarching framework, any description of the absolute earliest moments remains a theoretical construct, an elegant mathematical possibility rather than an empirically verifiable fact, represents the earliest moment our physics can even hypothetically describe, leaving an immense, unknowable chasm between time zero and the very beginnings of calculable reality. This frontier underscores a crucial distinction. Science excels at explaining how the universe operates and evolves within its established laws, but when confronted with the origin of those laws, or the ultimate source of existence itself, it enters a domain where its empirical tools are inherently limited. We cannot conduct experiments on the creation of universes, nor can we observe the precise conditions of a pre-Big Bang reality, assuming such a reality even existed in a conventional sense. Our pursuit becomes an archaeological dig in the dark, piecing together fragments of theoretical consistency and indirect observational clues, hoping to reconstruct a picture of something that may be fundamentally unobservable. Yet, this humility in the face of the unknowable does not diminish the scientific endeavour. It elevates it. The very act of pushing against these limits, of constructing elaborate theoretical models, of devising ingenious experiments to seek the faintest echoes from the earliest cosmos, is a testament to humanity's insatiable curiosity. It is in this relentless questioning that we expand our intellectual horizons, refine our understanding of reality, and glimpse the potential for entirely new physics. The quest for a unified theory of quantum gravity, the ongoing for anomalies, these are not futile endeavours, but vital probes into the deepest layers of existence, each step a testament to our profound drive to comprehend the universe. The creator of the Big Bang, therefore, may not be a single entity or a singular event, but rather a symphony of inherent potentials, a self-organizing principle embedded within the most fundamental and elegant sense, simply is, its very existence and its laws inextricably linked, without need for an external first push. This perspective challenges anthropocentric notions of creation, inviting us to consider a cosmos that operates on principles far more subtle and interwoven than a simple chain of cause and effect. It asks us to confront the possibility that the universe is not an artifact, but a continuous process, an eternal unfolding of possibilities constrained and guided by an underlying, perhaps eternal, framework of laws. Ultimately, the journey to understand the Big Bang's origin is more than a scientific investigation. It is a philosophical odyssey into the very heart of existence. It compels us to ask not just about the universe, but about ourselves. What does it mean that we, collections of atoms forged in stars that arose from this very Big Bang, possess the capacity to ponder such monumental questions? Our ability to formulate these paradoxes, to construct these intricate theories, to feel awe in the face of the infinite unknown, may be the most remarkable emergent property of the universe itself. It suggests that consciousness, in some profound way, is an intrinsic part of the cosmic tapestry, capable of reflecting upon its own origins. So, as we stand at this precipice of knowledge, looking back at the Big Bang and peering forward into the theoretical constructs of what might lie beyond, we are reminded that the universe is not just a collection of facts to be catalogued. It is a living, breathing mystery, a grand narrative that continues to unfold, revealing ever deeper layers of complexity and wonder, may never yield a simple, definitive answer, but the relentless, awe-filled pursuit of that question is perhaps the most profound journey humanity can undertake. It is a quest that transcends the boundaries of science and philosophy, uniting us in a shared intellectual and emotional endeavour to comprehend the infinite, to grasp the ungraspable, and to recognise that in the enduring enigma of creation, we find our deepest connection to the cosmos itself. The universe, in its silence, whispers profound truths, and we, the curious, continue to listen.